Have you ever seen an egg unscramble itself?
Of course not. It just feels wrong, doesn't it?
We know in our gut that the universe doesn't go from messy to neat. It goes from order to chaos. That's a fundamental law of physics called the second law of thermodynamics or entropy. The universe tends towards mush. So here's the puzzle. If the universe loves mush, how did we get all this incredible complexity around us? Think about New York City, with its billions of different products, with the nearly 7 billion people connected across the globe. How is any of this possible? The universe can create complexity, but it's really hard. It happens in special pockets with what we call Goldilocks conditions. Not too hot, not too cold, but just right. In these pockets, simple things can become slightly more complex, which then allows for even more complexity to build, step by step. We call these steps thresholds, and with each new threshold, things get trickier, more fragile. The Goldilocks conditions get stricter. As incredibly complex beings, we need to understand this story. It's the story of how the universe builds, and it's what we call big history. To tell it, we need to go back to the very beginning of time. Let's wind the clock back 13.7 billion years. Imagine nothing. No time, no space. Then bang! A universe appears smaller than an atom, incredibly hot, and expanding at an insane speed. In the first second, energy shatters into forces like gravity and congeals to form the first particles of matter. Fast forward 380,000 years. The universe is now filled with simple atoms of hydrogen and helium. It's basically a giant uniform cloud, but not quite. Tiny temperature differences, just 1,000th of a degree, were enough. Gravity, being stronger where there's more stuff, started pulling these clouds together. As the clouds compressed, the centers got hotter and hotter. When the core temperature hit 10 million degrees, a new threshold was crossed. Protons began to fuse, releasing immense energy. Bam! The first stars were born. About 200 million years after the Big Bang, billions of stars began lighting up the universe, making it much more interesting. These stars would create the Goldilocks conditions for the next two thresholds. When massive stars die in supernova explosions, they forge all the other elements on the periodic table. That gold ring on your finger? Made in a dying star? Now, with a richer chemical pantry, even more complex things could form. Around new stars, these elements swirled together, forming dust, rocks, and eventually, planets and moons. That's how our solar system formed about 4.5 billion years ago. A rocky planet like Earth is vastly more complex than a star because of its chemical diversity. We've crossed another threshold, but the next stage gets even tougher. It introduces something much more fragile, but also much more creative: life. Life is all about chemistry. And for chemistry to work its magic, you need Goldilocks conditions. You need energy, but not too much, like in a star's core, and not too little, like in deep space. Planets are just right. You also need a variety of elements and a liquid, like water, where atoms can meet and mingle. Our early Earth was perfect. It had huge oceans, and deep below, volcanic vents provided heat and a rich mix of chemicals. Fantastic chemistry began to happen. But life is more than just chemistry. How do you make it last? Life's clever trick is that it doesn't stabilize the individual. It stabilizes the template, the blueprint that carries information and allows it to copy itself. That template is DNA. The DNA molecule holds the instructions for building a living thing, and it makes copies of itself, spreading that information. But the real magic of DNA is in its mistakes. About once in every billion copies, there's an error. This means DNA is constantly learning, finding new ways to build organisms, because some of those errors actually work. Over 4 billion years, this process has built incredible diversity. For most of Earth's history, life was just single cells. But starting around 600 million years ago, multi-celled organisms appeared: fungi, fish, plants, reptiles, and of course, the dinosaurs. Then, 65 million years ago, a massive asteroid wiped them out. Bad news for the dinosaurs, but great news for our tiny mammalian ancestors who thrived in the aftermath. We humans are part of the evolutionary pulse that followed. Humans appeared about 200,000 years ago, and I believe we represent a whole new threshold. Why? Because while DNA learns, it's incredibly slow. It had produced organisms with brains that could learn in real time, but when they died, their knowledge died with them. What makes us different is language. Our ability to communicate is so precise that we can share what we learn and store it in our collective memory. This knowledge accumulates from generation to generation. This is what I call collective learning. It's our superpower. We see it from our earliest days as humans migrated from the African savannas to deserts, jungles, and even the Siberian tundra, learning and adapting. Then, 10,000 years ago, we learned to farm, creating a huge energy surplus. Populations grew, societies became larger and more connected. In the last 500 years, we started connecting globally, creating what is now like a single global brain of nearly 8 billion people, learning at warp speed. The discovery of fossil fuels in the last 200 years gave us another massive energy boost. Together, collective learning and fossil fuels explain the staggering complexity of our modern world. So here we are, we've journeyed 13.7 billion years. It's a powerful story where humans play an amazing creative role. But it also comes with warnings. Collective learning is a force we may not fully control. I remember the Cuban Missile Crisis, when our entire world was on the brink. Those weapons are still here. And now we re-burning fossil fuels so fast we re-threatening the very Goldilocks conditions that allowed our civilization to flourish. Big history shows us our complexity, our fragility, and the dangers we face. But it also shows us our power. I want future generations to know this story, to understand the challenges and the opportunities of this unique moment in our planet's history. That's why we're building a free online curriculum to give them the tools they need to navigate what lies ahead. Thank you for listening.